An analog-to-digital converter is a technique which converts a continuous analog signal into a sampled numerical values representing the original signal. The input to an analog-to-digital converter ADC consists of a variable voltage. The system generates digital values which are a combination of binary 0 and 1. ATmega32 has 8 such converters inbuilt. These built-in ADC can provide up to a 10-bit result value. Let's see more details of ADC and its applications. ATmega32 provides 8 ADC channels. You can use any one channel out of these 8 in your application. These channels can accept a voltage between 0 to 5 volts. We can configure ADC output in 8-bit format or 10-bit format. In 8-bit format, we lose 2 bits from the lower side of byte. This affects in a loss in resolution or less accurate results. Imagine that we have configured ADC 0 channel to read a voltage range with 8-bit output format. The lowest level of input analog voltage will result into numerical value of 0 and the highest allowed input analog voltage will generate numerical value of 255 as output of ADC. There are simple steps to work with ADC. Let's explore them now. There are simple steps to work with ADC. First step is to keep your hardware ready with one of the ADC channel connected to analog source of supply. You can use a temperature sensor or a variable preset which is provided on your experiment board. On software part, you can select a particular channel to which you have connected the voltage source by setting bit 0 to bit 4 of ADC SRA register. You can enable ADC feature by setting 7th bit of ADC SRA register. Clock to ADC has to be set by specifying prescaler value. Finally, you can start ADC conversion by setting 6th bit of ADC SRA to high. You will have to monitor this bit till it becomes 0. Once it becomes 0, you can read the converted value from ADCL and ADCH register. ADMUX register is used to specify the reference selection and channel selection. ATmega32 provides an internal reference of 2.56 volts. This indicates the center point of the conversion value. We can provide an external voltage reference. To keep our learning simple, we will use internal reference. To select internal reference, bit 7 and bit 6 of ADMUX register has to be set to high. You can specify the ADC channel usage by setting bit 0 to bit 4 as per the table shown on your screen. The ADLAR bit is used to specify the 8-bit or the 10-bit output format. If you want to use 8-bit output format, set the ADLAR bit. Look at the single-line source code on your screen in blue text. This configures ADC channel number 2 with internal reference turned on to provide a 8-bit output. The converted value of the analog signal will be stored into ADCH register in 8-bit format. The next screen will explain you about enabling ADC and starting conversion. Use ADC SRA register to enable ADC, start conversion, enable ADC interrupt, specify clock prescaler. Let's learn it one by one. To enable ADC, set 7th bit to high. To start conversion, set 6th bit to high. To check if the conversion is over, check if 6th bit is low. Low state of 6th bit indicates that the analog to digital conversion is over. To enable ADC conversion completed, interrupt, set 3rd bit to high. To use the interrupt, do not forget to enable global interrupt bit 2. Bit 0 to bit 2 are used to specify the prescaler, that is the division factor for the ADC clock. To specify a prescaler, you can use the values as shown in the table. The 5th bit ADATE is used to specify the advanced feature of ADC conversion process. If you want to start the conversion automatically, for example as and when time 0 overflows or external interrupt occurs, you have to set the 5th bit to high. To further specify as which particular action has to trigger the ADC conversion, use SFIOR register to do so. Single-line source code indicated in blue text on your screen enables the ADC and sets prescaler as 8. Next screen will teach you to start a conversion and read the result. Bit 6 of ADC SRA register is used to start the conversion. Same bit indicates about the conversion complete. Set this bit to high to start the conversion process. Read this bit till it becomes low, to wait for conversion to complete. The source code lines in blue color demonstrates the conversion. First line that the source code sets the ADSC bit that is 6th bit and starts the conversion. This uses an OR operator to retain the old values of ADCSRA register and further set the bit. On second line, while loop monitors the same bit. Let's understand the code written inside the while loop. There are two parts inside the round bracket of while loop. These two parts are indicated by two separate curly brackets. One part is indicated by a red-colored curly bracket and other by a green curly bracket. Let's understand the right part first. The double less than sign indicates the left shift. The sign will shift the value 1 to left by 6 bits. Because ADSC is the 6th bit. This way the right part will result into value as shown in binary format on your screen. This value will be compared with the left part value of ADCSRA. ADCSRA already have some value. Refer the previous screen and this screen. You will notice that bit 7, bit 6, bit 1 and bit 0 are set. The binary in operation between these two values from left and right will result into a non-zero value till the conversion is in progress. As conversion completes, the 6th bit of ADCSRA becomes low and the value of ADCSRA is changed. The changed value of ADCSRA is shown on your screen in red color. The binary in operation between the changed value of ADCSRA and the right side value will result into the 0. This will break the while loop and the program will continue further. Next screen will teach you to read the conversion results. This is the total source code for your application. Connect 8 LEDs to port P and connect a variable resistance to PA2 pin. If you are using EDT experiment board, you can make these connections using a connector. If you are using AVR lit, then these connections are already made for you. The source code will read the ADC value and convert it every 200 milliseconds. The equivalent converted value is shown using LEDs. You can change in input voltage to ADC channel by trimming the preset using a small tip screwdriver. There are many such instances in our daily life where we need to read an analog data. For example, read and display room temperature on air conditioner panel, refer light level on a sports ground like cricket, read voltages and current using a voltmeter, monitor dB level at a particular noisy site, etc. In all these examples, the embedded applications monitor analog signals and displays equivalent numeric values. We will use ATmega32 to read temperature, red